Welcome back. This is Fundamentals of Micro Nanofabrication. I am Swayam from IIT Bangalore. Now, before we go ahead and sort of look at other components such as the susceptor, the chamber, the substrate, it might be useful to give a little thought to how exactly the CVD happens in its mechanistic detail. This is going to be a big portion, and it will span multiple lectures, and is arguably the toughest part of a CVD lecture. So, what I will try to do is I will break it down. So, if you look at the figure, for example, I have just taken the same CVD diagram as before, but now I have broken down the various processes that must happen in order for the CVD to occur. So, we have already discussed about precursors, and those precursors are in the gas stream here. And let me get my pointer. So, they are in the gas stream here. So, some way we need to figure out how this gas stream is actually flowing inside the reactor. So, we discussed some basics of fluid dynamics or viscous flow before. CVD is in the viscous flow regime. How exactly, however, this gas flows really depends upon the geometry of the reactor, and this is where the reactor design and various other aspects come in. Once you have figured out how the gas flows inside a CVD reactor based on your application, then you must also look at how does the precursor actually make its way to the surface. In general, that actually happens through diffusion. Why not drift? You will sort of see in a minute. It is because we form a boundary layer, and then the only way things move through the boundary layer is by diffusion. Then the precursor must adsorb on the surface, then that surface it must do a surface reaction, form these particle nuclei which must nucleate to form a film, and then the byproducts must again diffuse back out into the gas stream, and the gas stream then flows out into your vacuum chamber. Right? So, let us take each of these components one by one. Right? Let us first talk about diffusion or getting the precursor to the surface. Right? Now, if you have a gas stream and you put a wafer in it, that wafer is a boundary in that gas stream, and that wafer probably sitting on a susceptor, which is another boundary on a gas stream. So, now imagine a situation where you have three wafers sitting on a susceptor, and this susceptor is one of the boundaries of the gas flow, and the other boundary is somewhere far away where I have not shown it. So, you are looking at a zoomed in image of your reactor very close to the susceptor. So, if you look at the velocity flow line, the flow lines of this gas chamber, inside this gas chamber, you will basically see a profile like this. Now, this is the same profile that we sort of discussed when we are talking about viscous flow in the previous lecture, and the reason of this unique shape is because of the no slip boundary condition. So, you assume that the gas that is very close to the interface does not have any velocity, and as you go further away from this interface, the velocity increases until it becomes V naught, which is the velocity in the middle of the flow. Now, because there is no velocity of gas near the susceptor or near the wafer, there is no way of transporting material to the wafer or transporting material out of the wafer. What essentially has happened is that there is a boundary layer that is formed, and this boundary layer is an arbitrary line that just represents the stagnant layer that forms on top of a wafer just because of no slip boundary conditions. Any fresh precursor and any byproducts must now diffuse through this stagnant boundary layer in order to get to the wafer and actually do the chemical reaction to do the deposition. Furthermore, this boundary layer is not uniform. The boundary layer might be very small at the start of the boundary, but as you go further along, the boundary layer tends to increase and become thicker. Right? So, the diffusion problem here is probably very easy because the layer thickness through which it must diffuse is very small, but the boundary layer here is much thicker. So, the diffusion process is harder here because the distance that the material has to travel is more. All right. So, what must now happen inside the whole reaction chamber is that here is your gas stream, and then there is this boundary layer or dead layer of varying thickness depending upon the distance that has formed, and the species must move from the gas stream to the wafer surface and must also do the same thing on the way out. So, what is the shape of this boundary layer? What is the thickness of this boundary layer? Is a very important aspect of a reactor design. If you solve the simple laminar flow equations in this system, you will actually see that the boundary layer is approximately given by this formula, where it depends upon the viscosity of the gas, it depends on the density of the gas and the velocity of the gas in bulk. Now, this V naught is the velocity, the unmitigated velocity, the velocity far away in the middle of the chamber. For a given reactor, you can define a certain Reynolds number, it is called RE of the reactor. It is a slightly different formulation, but it essentially measures how easy it is to flow gas through a reactor. Now, this is very closely related to the concept of a boundary layer, because a reactor that has a very thin boundary layer, you can imagine, will have a very small amount of stagnant layer. So, most of the reactor, the gas can flow easily, right. It is only mitigated in the boundary layer. But if a certain reactor has a very thick boundary layer, then the gas must feel a lot of impedance, because the boundary layer is not available for it to flow. So, the actual gas flow is restricted in a narrower region. So, if you were to calculate a rho average for a simplified case that I am representing here, which is the one dimensional case, where you have a boundary layer that starts from 0 and increases as you go further into the reactor. So, the boundary layer rho average is just the simple first moment of this equation. You can do simple math and you basically realize that the boundary layer thickness is directly proportional to L, where L is the length of the reactor. So, L is the length in this direction along the blue, and RE reactor is the constant that captures the ability of gas to flow inside this reactor. It depends upon what are the gases that are flowing inside the precursor, which is hopefully a constant. It will depend upon what velocity the gases are flowing inside the reactor, which is constant because you have fixed the pumping and the pressures. So, remember, the velocity of the gas depends upon the pumping pressure by the Ohm's law of gases. We looked at it in the last lecture. So, those same parameters will now give you your RE reactor. The viscosity and density of a liquid are slightly different from viscosity and density of a gas. So, typically viscosity mu, if you assume kinetic theory of gases, is given by this formulation, and the density is given by that formulation. In both cases, they are temperature dependent quantities. Viscosity tends to increase with temperature for gases, and density tends to decrease temperature with gases, partly because density is proportional to pressure, and at high temperatures the pressure tends to be lower. So, overall the boundary layer, which depends upon both mu and rho, has this formula where it is T to the power 3 halves dependent on temperature and inversely dependent on pressure. Over, however, you realize that neither of these quantities are exponentially dependent or very critically dependent on temperature or pressure. The boundary layer changes depending upon what temperature or pressure your growth is happening, but it does not change by an order of magnitude. So, it is a weak polynomial dependence, right, which is a good thing, because CVD often is done over a very wide range of temperatures and pressure, and if the boundary layer kept changing, then all the parameters that we have to do in the optimization of the CVD would also keep changing, and it would be very hard. Thankfully, that is not the case. Now that we have understood that there is this stagnant boundary layer of various thicknesses, but a stagnant boundary layer that forms on top of a wafer, we can do a little bit more in terms of growth mechanism. Now, those of you who remember the lecture on native oxide growth will find this to be eeringly similar. In that also we had assumed that there is a gas flow region, then we had assumed that there was a certain region through which the precursor must diffuse, and then we had talked about the reaction happening at the substrate. The only difference was that instead of the boundary layer, in that case the diffusion was happening through silicon dioxide, and instead of the reaction happening on top of the substrate, the reaction was occurring between silicon dioxide and silicon, right. So, buried interface, not at the top of the interface. And in that case, we had completely ignored the gas flow. I had said that it is not important, and let us assume that the gas concentration outside is constant. In this case, we can't assume that, right. So, what is happening here is that there is a concentration of gases beyond the boundary layer that we can assume to be constant, but then diffusion must occur through the boundary layer, right. and then the material must get to the top of the deposited film where the reaction will occur and the film will form. And these two fluxes, one is the flux of diffusion and one is the flux of surface reaction, must be equal under equilibrium, right. So, if F1 must be equal to F2, how can we further model this? By through this, because you see diffusion is given by Fick's law. So, F1 the flux F1 must be given by Fick's law, which is this, which is simply the diffusion coefficient multiplied by the gradient. To first order, we can assume this to be a simple first order characteristic where there is a flat lying gradient. So, it is simply Cg minus C naught by delta, where delta is the boundary layer thickness, C naught is the concentration at the substrate, and Cg is the concentration of gas in the middle of the reactor. This is often called Henry's law. This d by delta is converted into a constant called h for ease, and for a given reactor the h is unknown. The F2 once again is a chemical reaction. So, chemical reaction is a first order, assuming first order kinetics would have a relationship like this, which is K into C naught, where C naught is the concentration of the reactant at the substrate. Now, K is a surface reaction rate constant, and if F1 must be equal to F2, you can do a little bit of math and come up with the growth rate, where the growth rate is nothing but Cg, which is the concentration in the gas, divided by n, where n is the number of atoms of deposited material per unit volume or atomic density, multiplied by 1 over 1 plus h and 1 plus k. Now, supposing you had multiple precursors and not one, things become a little more complicated. So, supposing you had multiple gases in reactor, what must happen now is that you must talk of each individual component. So, the way this is mathematically handled is that the concentration Cg, which is the number of atoms per centimeter cube in the gas, can then be converted to pressure, because pressure is what we actually measure. We do not really measure concentration of gas molecules, we just measure pressure, which we know is proportional and equal and related to Cg by this expression, where Kb is the Boltzmann constant. Now, this pressure is there of each gas, but then you also have Dalton's law of partial pressure, where the total pressure is nothing but the sum of all these component pressures, right. Now, so if Pi is the partial pressure of each precursor, then you can also write this, where the fractional concentration of a certain gas is nothing but the partial pressure of that gas divided by the total pressure. So, these concentrations can now be converted to pressures, and here y is nothing but the ratio of partial pressure to total pressure. So, that growth rate equation that I showed before can then be written in terms of components that we actually control, which is pressure, temperature, Boltzmann constant, which is a constant, n, which is a material property, multiplied by the Henry's law constant, and the K, which is the reaction rate. This equation is extremely useful, and the first generalization that we can actually get from this is that to observe that growth rate depends upon the total pressure. This is constant across all CVD. If you want to increase your growth rate, you must increase your pressure, right. If we analyze this further, we can now realize that there are once again two regimes, and again those of you who remember the native oxide lecture would find this familiar, where we can take this take the equation and assume two cases, one where the H is much greater than K. In that case, what is happening is that diffusion is very fast. If diffusion is very fast in a process and two processes are happening in series, then diffusion is not the bottleneck. What is the bottleneck? F2 is the bottleneck, that is the reaction rate is the bottleneck. So, growth in this case is limited by how fast we can actually do the reaction at the surface, and in that growth rate can be given by this equation. Now, this K is the chemical reaction rate, which by Arrhenius equation must be exponentially related to temperature. So, you can convert K into K naught e to the power minus E A by RT. Overall, if you look at this expression, you realize that it is linearly dependent on pressure, but is exponentially dependent on temperature. So, the growth in the reaction rate limited regime is extremely sensitive to temperature. Just 50 degrees change in temperature up or down can actually change the growth rate by orders of magnitude. The other case is where K is much larger than H. So, in this case the F2 is not a bottleneck, the reaction can happen at arbitrarily higher speeds. The problem is getting the reactant to the surface of the wafer, and the only way we can do that is through diffusion, and diffusion is slow. So, in that case we are limited by diffusion. So, it is called a growth limited by diffusion or mass transport, and in that case the equation is given by this expression where it is P total into Y into H, where H is nothing but d by delta, where delta is your boundary layer thickness. Now, if you look at this expression, you see that is once again proportional to pressure, but is much more weakly dependent on temperature. So, its dependence on temperature only comes because of this T and some dependence on D and some dependence on delta. All of these are polynomial. So, unlike the reaction rate limited regime, the mass transport limited regime is much more insensitive to temperature. Right? However, it is very sensitive to delta, and delta is very sensitive to the gas flow dynamics of the reactor. So, the flow inside the reactor, what is the velocity inside the reactor, etc. So, reactor design or the shape of the reactor is very critical in mass transport limited regime. The temperature is very critical in reaction rate limited regime. However, the pressure is one constant, right? The pressure directly depends, growth rate directly depends on pressure. So, pressure uniformity is sort of required in all manner of CVD. Thankfully, this is not too much of a problem. Gases tend to diffuse very quickly, so it is very hard to maintain too large a gradient of gaseous precursors inside the reactor. Gases tend to be uniform. So, that is not a problem. We will talk about some second order effects of precursor depletion, etc. later. So, overall your growth rate shows the following temperature dependence. So, now we have already looked at the expressions. I am just now plotting those expressions, and I am plotting it in the Arrhenius format, which is I am plotting it versus 1 over T. So, you have your two regimes. You have your reaction rate limited regime. This is the regime given by this dotted line, where the reaction rate constant Ks is the bottleneck, and it depends upon the temperature exponentially. The other is mass transport limited, where the reaction rate is very fast. However, diffusion is slow. So, the problem the bottleneck parameter is H, and for the sake of argument here, let us assume H is constant with temperature. In reality, it is not so, but let us for argument's sake say so. So, in that case, the growth velocity will be an independent function of temperature. So, it will be completely flat if you are in the mass transfer limited regime. At lower temperatures, because of this exponential relationship, invariably K's are very small. So, you often are reaction rate limited. As the temperature goes up, the value of K grows up, and at some point the value of K becomes higher than the value of H, and very quickly you enter a regime where now you are mass transport limited. Now, the diffusion is the bottleneck. The reaction rates are very fast, but precursors are not coming in, and then your growth rate sort of stabilizes to a flat value, and at that point increasing the temperature does not increase your growth rate. And somewhere in the middle you have this mixed phase where little bit mass transport limited, little bit surface reaction rate limited. In these two regimes, what are the characteristics of growth that we can expect? So, in this case, the growth is strongly controlled by diffusion to the substrate in mass transport limited regime. The limiting factor at high temperatures. So, at high temperatures, invariably the problem is getting the material to the substrate, and it is uniform if the gas flow is uniform, right. So, if the gas flow is uniform, the H is uniform, so the mass transport limited growth rate is uniform. However, if you are reaction rate limited, your problem is the reaction of the substrate. You are limited by the temperature, and it is uniform if your temperature is uniform. If you have temperature non-uniformity, the K changes, you get non-uniform deposition. However, if that is not the case, as long as the temperature is uniform across the wafers and on top of a wafer, you will have the same growth rate. You have a uniform growth rate. Now let's look into the mass transport limited regime into a little more detail. So some part of this must be obvious to you by now, that there clearly would be an effect of the boundary layer, because the growth rate is given by the partial pressure, which may be uniform, or sorry, the total pressure, which may be uniform. However, it depends on d as well as delta. Now delta is the boundary layer which changes from the left hand side of the reactor to the right hand side of reactor, but also changes across a wafer, right. So if this is a wafer, the edge that is facing the gas flow will have a smaller boundary layer, the edge that is trailing the gas flow will always have thicker boundary layer. So as the delta changes, so with the edge, so would be the growth rate. So the deposition at this edge of the wafer would be very different from the deposition at this edge of the wafer. So there is non-uniformity just because of non-uniformity in delta. But even d is not uniform exactly, right, because d with respect to temperature tends to have this dependence. This is called Hammond's law, where it depends on 3/2 on temperature and linearly on pressure, or rather the ratio of partial pressure to total pressure. So overall, if you look at H, it has both the dependence of d and delta. So overall it tends to have H also tends to have a 3/2 dependence on temperature. Here I assume that delta is constant with T and P. Just a couple of slides before I had shown that that is not exactly the case. So is this formula exactly true? Probably actually true, exactly no. But in general, reactions tend to practically show this. There are a lot of second, third order effects that happen, so it's very hard to give exact exponents. The take home message here is that there is some weak polynomial dependence. Whether it is 3/2 or 1.6 or 1.8 or 1.2 really depends upon the details, but there is some weak polynomial dependence of Henry's constant on temperature. So overall, the growth rate on an average depends upon the d average and the delta average. So we already have discussed d has around d 3/2 dependence, and the delta average, which is the average thickness of boundary layer, is related to the Reynolds number of the reactor, which is related to the velocity of flow inside the reactor. Now it is useful to sort of look at what happens if we increase V naught. So supposing you took a same reactor and just pumped it harder, or you created a larger pressure differential between the two sides of the reactor, so more gas was flowing through it, or you increased the conductance of the reactor. You did something to increase the velocity of the flow. So if you do that, then your Reynolds number will increase and your boundary layer will decrease. So the boundary layer will become thinner, and if the boundary layer becomes thinner, then diffusion becomes higher, and at some point you stop being mass transport limited, right? Because mass transport limited assumes that the diffusion is the bottleneck. But if you keep reducing the diffusion coefficient, if you keep making the diffusion faster and faster, at some point you will not remain mass transport limited, you would become reaction rate limited. So that is what I am trying to show here, that you are mass transport limited for a certain range of velocities, but beyond a certain point you become reaction rate limited. And this transition can also occur at higher temperatures, because at higher temperatures, once again, the growth rate becomes faster. Why does it become faster? Because the d is larger, but if d becomes so large, then the diffusion is not the bottleneck and you again become reaction rate limited. Now supposing you were to make a practical system that works under mass transport limited growth, right? So your goals would be twofold. One is that you would want to create a system which has as high a growth rate as possible, because that saves time, and time is money. And the second is you want it to be uniform. So what can you do to, given all the non-idealities we have discussed, to actually get there? So the first is to just notice this delta, right? Now the growth rate is inversely proportional to the thickness of the boundary layer, because the thicker the boundary layer, the more the film has to diffuse. The thicker the region, the gas has to diffuse. So what can we do to reduce this boundary layer? The easiest thing we can do is increase the velocity of flow, right? The higher the velocity of flow, the lower the boundary layer. And higher V naught simply means that we design a reactor with a higher Reynolds number. But there is a limit here. We discussed during the laminar flow lecture that at very, very high Reynolds numbers, the flow becomes turbulent, and when the flow becomes turbulent, then all bets are off. There are other kind of non-uniformities that occur. So there is an upper limit to how fast V naught can be. Also at very high V naughts, you tend to become reaction rate limited, as I just showed in the previous slide. The second goal is to keep whatever value of delta we have constant across the wafer. The easiest way that is achieved is by loading the wafers at an angle. So what you are doing is, what you achieve doing that is that you change the velocity of the gas as it goes from left to right. So the effective cross section of the reactor is higher here, the effective cross section of the reactor is lower here. Since mass cannot be created or destroyed, the effective velocity must be lower here, and as you go from left to right, the velocity must increase. And as the velocity must increase, you can come up with a angle or a shape where the increase in the velocity exactly compensates for the increase in distance, overall keeping delta x constant. So keeping wafers at an angle is the easiest way to get a relatively uniform boundary layer and hence relatively uniform deposition. Overall growth rate looks something like this, where we have various precursors and we are looking at what is the temperature dependence in 1/T plot of that precursor versus of that precursor, the growth rate we get with that precursor versus temperature. Since this is 1/T, this represents high temperature region, this represents lower temperature regions. So at low temperature regions, you are often limited by reaction rate. So you have a exponential dependence which in the log scale looks linear. So this is a log scale growth rate. So this looks linear, and at some point you transition into the mass transport limited regime where you have a 3/2 temperature dependence. Different precursors will give you slightly different curves. In general, as the stability of the precursor increases, it tends to decompose slower, which means it has lower growth rate. So as you go from silane to dichlorosilane to tetrachlorosilane, the growth rates all keep coming down. A little note on this diffusion coefficient D. At this point, I have used D in several contexts. Those of you who have taken a course in devices may know D of electrons in silicon is around 35 centimeters square per second. We use this in device physics. We looked at diffusion of phosphorus in silicon when we were doing diffusion. We looked at diffusion of oxygen and silicon dioxide when we were doing growth of silicon dioxide, and right now we are talking of D of oxygen in oxygen when we are doing it CVD. So be very careful with these very different Ds. Always they mean different things. They have all different orders of magnitude, right? This is -14, this is -9, this is 0.18. So be very careful in using the correct D to do a calculation. Always ask the question diffusion of what, in what, and at what temperature. All right. With that, I'll just list out the various types of CVD equipment you can actually design. There's a plethora of techniques. There's hot wall versus cold wall. There is atmospheric pressure CVD versus low pressure CVD, metal organic CVD, laser CVD, PE CVD, ALD, etc. We'll discuss each of these in a couple of slide level detail next based on the concept that we have done in this lecture. So see you next time.